Welcome to Week 1, Review and Drag. I'm excited to be back for a new semester of Classical Mechanics for Educators. So today what we're going to be doing is we're going to be deriving the kinematics equations, and we're going to be using Newton's laws to calculate the motion of an object subject to air resistance. These first 2 weeks are going to be a little bit of review just to get you back into the swing of things. And I hope you will share feedback with me on whether this was too fast or too slow for you and how much you remember, just because I know just over the break you can get rusty, or if you're new to the program, I definitely need to know how you're feeling about this. Alright, so let's go ahead and get started with deriving the kinematics equations. So the kinematics equations that we use in intro physics are for constant acceleration generally. Okay, so acceleration is a constant, and we want to find equations for velocity as a function of time and for position as a function of time. Well, we do know that acceleration is the first derivative of velocity, and that acceleration is the second derivative of position with respect to time. So if we want to find velocity, we need to integrate acceleration. And if we want to find position, we need to integrate velocity. Okay, so here's your warm-up. Is doing some not too difficult integrals, but totally in symbolic form. We're not going to be using a lot of numbers. That's something that you'll need to get used to this semester. And the reason we don't use a lot of numbers is because it allows us to derive more general formulas that we can apply to a lot of situations, and it makes it a little easier to see exactly what each parameter causes to happen. So here's what I want you to do. So go ahead and find velocity as a function of time and position as a function of time by doing these integrals. Acceleration is just a constant a, and make sure not to forget about your constants of acceleration. Alright, and if you're new to my classes, when I give you something to do, what I want you to do is pause the video, try it for yourself, and then press play when you're ready to go. If you're not quite sure what I mean or where to start, you can go ahead and press play, and then you can pause whenever you feel like you know what you're doing. So velocity is the integral of acceleration with respect to time. So we just get a times time plus an integration constant. Now, to get position, we integrate velocity. So when we integrate that, we do at squared over 2 plus c1 times t plus another integration constant, c2. Now let's figure out what those integration constants are. Alright, so you recognize these equations. You probably know what c1 and c2 are. Let's work this out. So I'm going to give you some initial conditions. And this is something you remember that we worked with differential equations, that we used initial conditions to find constants. And we just did some integrals, but you can think of integrals as the solution to the most basic differential equation there is. So here are your initial conditions. The initial velocity is called v naught, and the initial position is called x naught. So what I want you to do is to use your initial conditions to solve for c1 and c2. So use the techniques we use for differential equations to solve for c1 and c2. Alright, so pause, try this out, and then we'll go over it together. So we have our equations. Okay, so velocity is acceleration times time plus c1, and that equals v naught. So this is 0 plus c1, so c1 equals v naught. And position at 0 is 1/2 at squared, so it's a over 2 times 0 squared plus c1 which we now know is v naught, times 0 plus c2 equals x naught. So this term is 0, and the middle term is 0, so that just leaves us with c2 equals x naught. So that tells us that our final equations, our velocity as a function of time is at plus v naught, and position as a function of time is 1/2 at squared plus v naught t plus x naught. These are our familiar kinematics equations. So I'm curious to know, how do you introduce equations to your students? If you're teaching calculus-based physics, do you go through this derivation with them? How do you introduce them to your algebra-based students? What sorts of notation is the least confusing for your students? Because I know there's lots of different ways you can use knots or initials. Or do you use modeling to introduce the equations? I want to hear what you decide to do. Alright, so the next task, what I want you to do is to combine these two equations to get our familiar equation, v final squared equals v naught squared plus 2a delta x. Now you may use different notation for this equation than I do. There's of course lots of different choices you have, and I bet you've probably done this at this point, but just to make sure we're all on the same page, go ahead and derive this equation from these two equations. Alright, pause the video and do that. Okay, there's not enough room for me to get this all done on the previous page, so I'm just going to go ahead and recopy our equations over here. Okay, the first thing I'm going to do is solve the first equation for time. Now my notation looks a little cluttered because I have v as a function of time instead of v final. But I think it's really cool to think about it this way. V final could be at any time. Okay, let's plug that in, although this notation is a little cluttered. Okay, so this a cancels out with one of these a's. The next thing I'm going to do is multiply the whole thing by 2 times acceleration. And I'm going ahead and multiplying this one out. Okay, now I'm going to subtract this term 2a x naught from both sides. I'm going to multiply this term out. There was temporarily an error right here because I forgot to write a 2. Okay, so what do we get? Well, this minus 2v naught v cancels the 2v naught v. V naught squared minus 2v naught squared is minus v naught squared. Alright, now this is looking more like our familiar equation, where x of t minus x naught is delta x. Here's our usual equation, where v final is v as a function of t. Okay, so I expect many of you have done this before. I want you to share with me how much of this you do with your students. I know one high school teacher I observed, they would derive all the equations together as a class, and then they would put them on the board, and they would leave them up on the board all year, every time as they derived them as a class. So the next thing we're going to talk about are Newton's laws, or more specifically, Newton's second law. Now you can technically derive all of Newton's laws from Newton's second law. It took me the longest time to figure out that Newton's third law is a consequence of Newton's second law. If you want to talk about that more, let me know. Okay, so we all know F equals ma. In fact, I have students coming into my class in college. They all know F equals ma. They don't necessarily know what it means, but they've heard of it. Okay. But in this class, this form of the equation is not going to be very useful for us. It's going to be more useful is in the form where acceleration is the derivative of velocity, or where acceleration is the second derivative of position. And which one of these forms is more useful depends on the form of the force. Now there's a new notation I want to introduce to you. Now last semester we were using the notation where you go v prime makes the derivative, but the The standard notation in classical mechanics is to use a dot. One dot means the first derivative with respect to time. We don't use this for derivatives with respect to position, we only do it for time. And so instead of having mx prime prime, we do mx double dot. I do not know the historical reason for why there's more than one set of notation, but this is what we use in classical mechanics. Alright, so we are going to spend most of our semester solving these two equations. And so I want to go over what we can do with these equations. What we do with our students, at least I teach University Physics 1. So that's the first calculus-based physics here at A&M Commerce. And we spend a lot of time drawing free body diagrams and then using Newton's second law to solve for what the acceleration is, and we have lots of numbers and we do all that. What we're going to be doing in this class is we're going to be setting up equations using Newton's second law. Then we're going to solve for velocity and position as a function of time or as a function of position, depending on the form of the force, what's going to be more useful. We're going to be thinking about how changing the mass changes the answer, or how changing the initial conditions changes the answer. We're going to leave everything in alphabet soup. We're going to be drawing graphs. We're going to be taking limits. So the way we work with this equation is different than what we do with our introductory physics students. Now, what I just said I think sounds way too abstract. Let's just go through an example and see what we can do with Newton's second law. So for our example, we're going to start by looking at an object that's subject to air resistance. I have my block. It's just sliding along a surface. I'm going to say that it's moving to the right. Its initial condition is that its velocity at time 0 equals v naught. Everything we do is going to be in letters. And this is so we can see how increasing and decreasing our particular parameter changes our results without having to do the equation over and over again. Now the only force we have to worry about for this problem is the drag force, air resistance. Of course, there's gravity and the normal force, but I'm only concerned about the horizontal motion, so let's just focus on that for now. We're actually going to get to three-dimensional motion later in the semester. Air resistance can take a lot of different forms depending on the fluid and the shape of the object. We're going to, in this case, use the approximation that the air resistance is proportional to the velocity. So it's going counter the direction of motion, so it's minus v, and proportional, L is our constant of proportionality, and that's going to depend on the shape of the object and the fluid and everything, in which case let's just say it's air. So we want to find velocity as a function of time and position as a function of time. And I don't do this sort of problem with my students in introductory physics because they haven't taken differential equations, and it does take differential equations to solve these. Doesn't mean you can't talk about these with students in, say, algebra-based physics. I do have some papers on this subject and how to talk about them with algebra-based physics, but I want you to share what you do with your students on this subject. Alright, so the first step in working out what's happening in this physical situation is we want to write the differential equation of motion. That means we write out either F equals mx double dot or F equals mv dot. In this case, because our force depends on velocity, we're going to use the v dot version. If our force depended on position, I would use the x double dot version. So we have minus LV equals mv dot. And if you want to write it out without the dot notation, that's m dv dt. And this is known as the differential equation of motion. Sometimes the differential equation of motion is simply referred to as the equation of motion. So now we want to solve for v of t and x of t. Okay, my box is kind of crooked. That's okay. I want you to do this. This is a differential equation you should know how to solve. But let me know how rusty you're feeling so I know what pace to take this class at for right now. Okay, so this is a separable differential equation. And after you find velocity as a function of time, you can integrate to get position as a function of time. And you can just leave it an integration constant for now, and after we have that form written out, then we'll use the initial conditions. Alright, go ahead and solve for v of t and x of t. Okay, here is our equation. It's separable, which means we want to get all the velocity parts on one side and all the time parts on the other side. It doesn't matter where you put the constants. I'm going to decide to keep them with the time part. Okay, remember L and M are constants. I know because they're letters, they kind of look like variables, but we're not treating them like variables because velocity and time are the ones that appear in our derivatives. Velocity is our dependent variable, time is our independent variable. So now we need to integrate both sides. Alright, so we only need an integration constant on one side because if I put on both sides, I could just absorb them into one constant. Alright, so let's work this out. When I write exponent like that, that's just me doing the exponential. I'm going to be writing it like this just because it's easier to read, because when I write a whole lot of stuff in subscripts, it gets hard to see, especially in the videos. So this is just the same thing. And I hope you remember that when your integration constant ends up in the exponent like that, that this is the same thing as having the integration constant out front. Alright, now let's solve for position as a function of time. So we just have to integrate this one. Oh dear. So I've resorted to putting my constants in the exponent, so they're probably hard to read. That says minus L over mt. So if I integrate that, I'm calling this C2. I will retroactively put C1s in the previous equation. Okay, now let's talk about our initial conditions. So our initial condition was that it's moving to the right with the velocity v0. We can define x equals 0 wherever we want. So I'm going to define x0 to be x equals 0. I'll define this to be the positive direction, this to be the negative direction. So v at time 0 equals v0, and x at time 0 equals 0. So we have here velocity as a function of time with one unknown constant, and position as a function of time with two unknown constants. So C1 and C2 are two unknown constants. We have two initial conditions, so we can find C1 and C2. So I want you to find C1 and C2 using the initial conditions, which I'm now going to abbreviate IC. Pause the video, give that a whirl. Alright, I'm going to start with velocity. So I know that velocity at time 0 equals v0. So if I plug in 0 into my equation, the exponent of 0 is 1, so this just equals c1 equals v0. So c1 equals v0. This means that x of t becomes minus mv0 over L times the exponent. And we plug in x of 0 at time t equals 0. We get the exponent of 0 plus c2, and this should equal 0. Well, we know that the exponent of 0 is 1, so it's mv0 over L plus c2 equals 0. Therefore, c2 equals mv0 over L. So then x of t becomes, I like to clean this up and put together my terms. All right, so here are our solutions. Let's copy these over on the next page. Okay, so we want to physically interpret our solutions. So I remember the first time I learned all this material at this level. I would get these equations and then I'd say, "Problem done, hooray." You don't stop here. You haven't stopped to think about what this means. So there's a couple different techniques to thinking about what these mean. Alright, velocity, that equation is a little bit easier to interpret. You can recognize this as exponential decay and position as 1 minus exponential decay. So one way you can do this is by checking limits. So this is something physicists do a lot, is we'll take the limit as time goes to infinity and see what happens to our equations. Now physicists tend to be kind of sloppy about this. So we go like this. X, when time is infinity, equals what? Velocity, when time equals infinity, equals what? Technically, you should be using limit notation. But because we are being physicists who just want to see what our equation does, I'm not going to worry about it. So go ahead and try to think about what these equations equal when time equals infinity. If you're not sure what I mean, just go ahead and press play and watch me do it. But I think you can give this a pretty good thought of what happens when time gets very, very large. Okay. So what do we have? 1 minus the exponent as time goes to infinity. So this is an exponential minus exponential. E to the minus infinity is 0. So it just becomes mv naught over L. And what do we get for velocity? So this is a negative exponential. That goes to 0. So this goes to 0. So this tells us velocity is going to 0. That means eventually the object stops moving. And x as a function of infinity tells you that it goes a total distance of mv naught over L before it stops. Well, hold on. What does that mean? Does it make sense that mv naught over L is a distance? Okay, let's back up just a minute. What's up with L? So I want you to stop and think, what are the units of L? We know that a force equals minus L times V. So I want you to use dimensional analysis with this equation to figure out what the units of L are. Alright, pause the video and figure that out. Okay, so force has units of newtons. We have something we're trying to figure out, and velocity has units of meters per second. So the thing we want to figure out must have units of newton seconds per meter. What is a newton second per meter? Well, a newton is kilogram meters per second squared. Alright, meters cancel, seconds left here. It's a kilogram per second. The units of L are kilograms per second. That doesn't make a lot of sense either. So it's kind of hard to think about what L is exactly. It's a proportionality constant that represents what we see happening in real life. Modeling drag is not easy. Actually figuring out what these constants need to be, it's not straightforward. So we also end up in situations with funny units. And drag can be modeled with all sorts of different proportionalities depending on the object, depending on the fluid. So different drag coefficients have different units, and I want you to make sure you're comfortable figuring out what that is. Now, of course, this is going to work out to having units of distance because it has to, because we just derived it this way. So mass is kilograms, V naught is meters per second, L is kilograms per second. If we work all that out, we get meters. It's kind of weird, huh? Let me know what you think about it. Okay, the other thing physicists normally do to understand what their answers mean is graphing their answers. But we don't have numbers. Okay, so if I need to plot something and I need to use a computer tool to do it, and I'm not sure what the numbers are going to be, I'll just make up a number. Say I'm just using a computer tool, I'll just say L over M equals 1. I just set a lot of things equal to 1, and then my computer tool can do it. But I don't need to do that for this one because I understand exponential decay. But maybe you're a little rustier on that front and you need to use computer tools. That's fine. I'll be interested to hear what tools you like to use for graphing. So x of t is 1 minus an exponential. So I'm doing upside down exponential decay. And I already calculated that as t approaches infinity, that it approaches mv naught over L. And velocity as a function of time is exponential decay. I know what that looks like. It goes to 0. And it starts out at v naught. Okay, so let's think about this. Does this make sense? So it starts out going fast, and then it slows down and eventually stops. Because we know that the slope of the position graph is velocity. So it's getting less and less steep, so it's slowing down. And our velocity graph shows that at first it's going fast and it's slowing down, and the rate at which it's slowing down decreases. Does that make sense? Yeah, it does, because the slower it's going, the less the drag force is, so there's less acceleration as it slows down. So this is always important to do, is to go back, look at your equations, think about their limits, look at their graphs, make sure they make sense. I'm betting a lot of you, and I know I've heard from some of you before, that you spend a lot of time looking at position, velocity, and acceleration graphs with your students. And I do too. And we can apply those same skills to making sure that these graphs work out the way they're supposed to. So I want you to share with me what tools you like to use for graphing, and if you want me to talk about more resources for what you can use to graph, because exponentials are relatively straightforward to graph, but sometimes you get a function that you're not accustomed to seeing and you don't quite remember what it looks like. And also something to think about is how does changing the mass or changing the drag coefficient or changing the initial velocity affect what happens in the end. So we see that increasing the mass will increase the distance it's able to travel. Increasing the initial velocity will increase the distance it's able to travel, whereas increasing the drag coefficient decreases the distance it's able to travel. You think about that. Does that make sense? I think it does. But the ratio of the drag coefficient to the mass is what determines the rate at which it decays. And that's something interesting to think about. And that's where I think, gosh, I would love to do an experiment and see what this means in real life. Alright, so the last thing I want to talk about is an alternate method for dealing with initial conditions, which I actually think is easier for a lot of these problems. Okay, let's back up. Okay, so we were solving a separable differential equation way back when, a couple of pages ago. Alright, and then we were going to integrate both sides and get an integration constant. Well, instead of doing that, we're going to do definite integrals. So time, we always set time to start at t equals 0 and go to time. It's a little bit funny because you're going to be plugging in time for time, t to t. If that bothers you, you can make the t inside the integral a t prime. But if you're okay with winging it, you can just leave it. And v gets integrated from v naught, our initial v, to our v as a function of time that we're solving for. Okay, let me know if that makes sense. It's going to give us the same answer. We're just putting in definite bounds. We're starting from t equals 0, where v is v naught. We're ending at time, that's our function of, where v is a function of time. We're going to do the same integrals we did before. It's just going to work out differently. So you should know how to do definite integrals. So go ahead and work this out for yourself and find v as a function of t. Alright, pause and try it out. Okay, So if I do this integral, I get minus L over M times t integrated from 0 to t, and I get log of v integrated from v naught to v of t. Alright, so this is minus L over M t minus 0, and log of v of t minus log of v naught. So this is minus L over M t equals log, if you know your log properties, this is v of t over v naught. So this gives us v of t over v naught equals the exponential minus L over mt. So multiply that out. Okay, so now we don't have integration constants, we just did definite integrals, and we get the same answer we got last time. Cool, right? I prefer this method myself, at least when I'm doing this sort of problem. Now I want you to find x of t using this method. So we know that position is the integral of velocity, but think about it this way. Velocity is the first derivative of position. Multiply the dt's over, do the integrals, but this time you're going from the initial x, which we're saying is 0, to the x of t we're solving for, and we're going from our initial v, and we're going from our initial time, 0, to our final time, t. Let's write this out on another page. It's getting a little cramped. Alright, so we have dx integrated from 0 to x, that's the initial position of x, to the final position of x, x of t. And then we have velocity integrated over time from our initial time, which is 0, to our final time, t. Again, you can make this t inside the integral a prime if that makes you feel better, but it doesn't really matter. And again, we set the initial position of x to be 0 just because it makes it easier. The only reason not to do that is when you're dealing with more than one object. And we're only dealing with one object right now. So, if we do this, then we have, and our equation for velocity came out to be, so go ahead and work this out to find your equation for position as a function of time. Alright, so let's work this out. So we get x integrated from 0 to x of t equals, and that's bounded from 0 to t. So we get x of t minus 0, exponent of 0. Well, the exponent of 0 is 1. So we have x of t. Okay, both terms have mb naught over L in them again. I'm going to start with a positive term. So we have a 1 minus exponent so we get the exact same answer we got last time, but just using a different method. Let me know what you think of the two methods. Which do you prefer? I like this one, but again, it varies depending on what the problem is. Okay, so I know from past experience that you all tend to like when I give you lots of examples to try on your own, but you know how it is when the problems start getting longer, it gets harder to give you lots of practice. But we're going to be doing more examples of working through. We're going to be doing more examples with air resistance in particular. We're going to be practicing interpreting our results. That's our physical mapping. If you remember the paper from Math Methods, we're going to spend a lot of time on our physical mapping. So let me know how this was for you. Was it too fast, too slow? What do you remember? What have you forgotten? We're all a little out of practice right now. It's the beginning of the semester, but we'll get warmed right back up. So post in the problem solving discussion and email me questions. I'm here to help you out. But talking to each other is just really valuable, so make sure you do that.